All right, welcome back to another episode of Bio to Bedside. This is episode 20, which is kind of crazy to think
Nice
about.
milestone.
Yeah, it is a nice milestone. We're pretty excited by the guest that we have to join us today, Adrian Veres from Dyno Therapeutics. Adrian, we first met in the flesh back at ASGCT this year. I was sitting on a couch and you you introduced yourself to me, which was awesome because. Yeah, I've followed you guys for a long time and was really excited to see the progress that you guys have seen. So quite excited for the conversation today. I guess to kick things off, Adrian, would you be able to tell us a little bit more about who you are and what you're doing?
Absolutely. Yeah, glad to be here. So I work at Dyno. I'm one of the co-founders, chief scientific officer. I lead the teams. Dyno is really focused on genetic technologies. We're building genetic technologies, and then we license them to gene therapy developers who use these technologies in their products. So far, our focus has really meant we've been 100% focused on AAVs, meaning we're engineering new AAVs that have new delivery capabilities. We're working in different organ areas. So we're working in CNS, in muscle, as well as in ocular delivery. And the emphasis there is just really creating a delivery platform that a gene therapy developer can take to really do three things. One is be able to achieve therapeutic delivery, meaning enough to have an effect, but do that in a safe way, and also in a way that they're confident will translate to humans. And so that's our platform. We started the company in 2018. This was actually built on years of work in the Church Lab at Harvard. And it's been a very exciting time to be building in the gene therapy space.
Right on. So yeah, tell me a little bit more before we jump into some of the main questions. Like, what was that experience of working in George Church's lab and spinning out a company? Obviously, it's a company known. It's a lab that's very much known for that. What was that experience like?
So I'll add a detail there. So I myself was not in the Church Lab. I was actually working in cell therapy at the space. I trained as a physician scientist, but ultimately decided to come in industry because it felt like that was the place where, as a technology builder, I could have the most impact. But Eric, our CEO and co-founder, is the one who joined the Church Lab for this. And Eric and I go way back. And we were both very passionate about really this ability to apply next-gen DNA synthesis and next-gen DNA sequencing to kind of have this loop where you could design new sequences, initially with like computational tools, then that became ML, that became AI, but design new sequences that do impactful things. And the core question was, what should we design? Like, where do you have the most impact? And one of really a key realization that was, credit to Eric early on, was amongst proteins. Huge impact to be had with AAV, because if you solve this delivery layer, that can actually be applied across a number of indications, across a number of contexts, and really maximize the impact. That was the thesis of Dyno from the start, and really now, 7 years in, we're kind of executing on that same mission.
Right on. So just before we get any further, thank you to everyone who has come today. If you have any questions for Adrian as the conversation progresses, by all means, feel free to put them in the chat, and we try to get to all of them that we can in the time that we have together. And also, if you're just joining again, thank you for coming. We're joined by the co-founder of Dyno Therapeutics, Adrian Veres, and we're going to be talking about about the approach that they're taking for AAV. For anyone who has joined, please feel free to let us know where you're coming from in the world. It's really cool to see just how global the audience is. So we always love to see that. So if you've got a couple seconds here while we're having a conversation, feel free to let us know where you're coming in from. So I guess to start off for you there, Adrian, what is the main problem that you folks are tackling?
Yeah, I think the main problem is that if you look at gene therapy, it's following a very similar pattern we've seen in biology time and time again, which is it's very hard for us until now. That's like now starting to change with AI, but it's very hard for us to create a completely new biological machine. But we're actually pretty good at repurposing something that exists. This could be a protein, could be a complex, could be even a cell, and like tuning it for our own purposes. And so AAVs are a really special vector. They're a virus that barely deserves the name because it really causes almost no effect when it's present in the body. That's really what makes it special, is that actually its interaction with the immune system is extremely small. It doesn't cause really any phenotype when the infection is occurring. And initially, it just goes pretty well to deliver. And the challenge of the field, we've been decades into this, has been how can you repurpose that for useful applications? If you want to deliver something to deliver, that's great. Many ways to get to deliver today. But if you're trying to get to something where it's hard to get to, like the brain, the challenge is how can you change the approach of the vector to get to the brain? And initially, for example, a lot of the focus was, can you get a neurosurgeon to just inject it directly in the right place? And that actually works quite well and is the basis by which we're starting to see interesting clinical results from this approach. But ideally, you could do this in a less invasive way. So for example, if you want to inject it intravenously and go to the brain, you have to do two things. You have to prevent it from going to the liver in the first place. That's what it evolved to do. But then second, you need to somehow make it go through the blood-brain barrier, reach the right neurons, and do so efficiently enough so that it's safe to inject. That's kind of the core challenge. And there's like sort of corollaries of this challenge in other target organs, in muscle or in eye. But really the idea is avoid where it normally wants to go, send it to the right place, and be able to utilize all the machinery that the virus is able to do to not just get to the cell, but actually get its payload expressed and stable for a long time, which then enables you to build a long-lasting therapeutic, which is the promise of gene therapies.
So I've got a pretty naive question. Is the ultimate goal to have like an intravenous AAV that can go wherever you want it to go? That seems to be kind of like the ultimate goal would be that, right?
Essentially, yes. And that feels very possible based on what we see today. I think in organs where there's very large unmet need, we've seen tremendous progress. And what we've learned from that experience, I think we could target it like organ by organ. Of course, maybe not, every organ needs a gene therapy. The spleen, maybe we just don't need it. But for many organs, right, you can imagine, and it's actually not just the organ, but it's often the cell type. Right. Being able to achieve that specificity is going to be a combination of the right AAV as well as the right regulatory components that enable that AAV to function in that organ.
Right.
Perfect. Excellent. So you'd mentioned CNS. So in the context of gene therapy right now, last week there was a death in a CNS trial with Capsid Therapeutics. What are your thoughts on that?
Yeah. So I think first of all, I think it's a reminder of just how brave. To me, I think of the families who participate in these trials understand the risks and the challenges involved, and I'm really touched by the bravery of everyone in this field, and that comes down to the unmet need. I think it's still really early days. We just don't know much except that this has occurred, and it's extremely unfortunate, really almost a worst case scenario here. Hoping to learn more as likely the investigators running the trial will themselves are learning more, and hopefully they share with the community so we understand what happened. Was this related to the therapy itself? Was this related to STXBP1, the actual disease itself, and how it interacted with the therapy? Was this a matter of the capsid, or was this a matter of the payload? Looking back at the field, typically we've been able to learn a lot from these unfortunate circumstances that require sharing the information. But of course, I think this is the exact opposite of what us as a field we're hoping for to see in this first time that BBB penetrant capsids were being used in the clinic.
Yeah, definitely. Very good. All right, perfect. Well, it's good to see we've got some people from Spain, India, and Germany all chiming in. Appreciate you guys. Thanks for coming. Again, if you have any questions for ourselves or for Adrian as we go through this really fascinating intersection of AI and gene therapy and using these together to make gene therapies that are going to be better for patients. If you have any questions, by all means, feel free to put them in the chat, and we'll get to them as quickly as we can. So just moving forward a little bit here, Adrian, right? So if we're thinking of the problems that are currently facing, particularly, right, the AAV gene therapy space, using a viral vector to deliver a genetic therapeutic to some portion of the body. We often kind of think of, like, obviously getting them to the right spot and nowhere else, ensuring that they're really potent once they get there, that they're high quality, but then also the cost of them as well, right? So we're thinking of basically, the precise nature of them actually being really good once they get to that precise point, and then also making sure that we can make them relatively inexpensive. So for Dyno Therapeutics and the approach that you guys are taking, especially with regards to AI, how are you starting to come at these big challenges inside of the field?
Yeah, I think what's interesting is all of those properties directly start by what the AAV sequence you're working with. And the thing that's interesting there is it's remarkably easy to state. AAV is really just a 700 amino acid protein. That's many components come together, copies of that 700 amino acid and subsections of it come together and form this shell that packages the DNA and then is able to, like, get it to the target nucleus. The consequence of that is you change those 700 letters, you make changes, you are going to get new properties. Because it's been a highly evolved, like, really well-engineered machine, actually most changes you make just break it. So you can't go in, because it has to do all of these functions, and evolution's really compressed all of that activity into a small, tiny virus of viruses. But that actually in turn makes it an amazing AI problem, because you can state it really precisely. You actually have this thing that's like, just put the right letters. You have this list of properties, which with the right technology that we've built at Dyno, you can measure. You can do this in primates, where you can put in many, like hundreds of thousands of AAVs and get extremely accurate measurements of how much of each of these variants went to the brain, to the liver, to other tissues. So you can make that measurement, and then you can build models that actually learn what are the patterns that govern this, that also enable you to go to the brain, but also to be manufacturable and ultimately optimize in the right direction. So it's really an extremely crisp AI design problem that we've been building on for years now, and that's really effectively working. Like, we see this time and time again when we design libraries at Dyno. You also put in rational designs. You also, every time you design a library, you also have your scientists come together with some ideas that you're testing. The reality is, often if you actually have an idea that you're testing and ask the design models to create solutions to that idea, they reliably make solutions that are much better than the ones you might craft yourself, because they can benefit from all that context. Ultimately,
so is there is there a risk that the primate biology is different enough that the AI is not going to be able to give us accurate results, like, for use in humans? Or is the physiology so close that we can get all the data for the AI from the primates, use that, and then have it replicate itself in humans? Or is there a risk there, a significant risk?
So I think it is biomedicine. So I think translation, we know, is we shouldn't expect it to be.
It's never one-to-one, right?
But the reason we've chosen to focus on primates is because we know that if anything will the highest likelihood of translation will start in NHPs, and that's where you want to start. But then over time, you can augment this information in interesting ways. So once you have an AAV that, for example, crosses the blood-brain barrier, it will do so by binding to a specific receptor. You can learn, you can identify that receptor is, or you can intentionally design it from the start, and then you can do experiments in vitro using the NHP version of the receptor or the human version of the receptors, and understand, like, is the interaction the same, is it different, and help you build that confidence. So when you go into human, you have the lowest risk of translation as possible. Does that guarantee everything? No. In some, but you can get to a state where the last thing you have to do is to do the human experiment. And that's where we want to go. Over time, I also think this is a place where AI can bring a big opportunity, which is learning how to transfer across contexts. And interestingly, this is actually an active discipline in the context of AI more generally. Like, you want to be able to transfer information across contexts, for example, video and text. There's something similar and arguably easier in transferring information from mouse to NHPs to different NHP species, and ultimately with the goal of predicting human with the highest performance. And in vitro human models play a role in that as well.
Excellent. So if we back up here a little bit, I really like that analogy, right? The AAV sequence essentially is 700 amino acids long, and based off of how you modify that, you can make it go into the brain versus into muscle, specifically into cardiac muscle versus going to the liver. And so I guess when we're thinking about the approaches that are taken to designing that 700 long amino acid sequence, where have other approaches failed when it comes to designing capsids?
Yeah, I think if you look back at the history of the field, it's quite interesting, because the most common approach, if you look at evolution experiment like guide design, you just try to make changes and then measure what happens. That's been very challenging. That works really well with maybe an enzyme or other types of proteins. Remarkably difficult to do with AAV. Going back to this point that, and actually we've measured this experimentally. This experiment was done in the Church lab at Harvard prior to founding Dyno. If you make individual amino acid changes, 70% of those just break the capsid. They will not allow it to package. So you have to be very smart about how you make those changes, and that's one change. And to get to the brain, you'll need more than one. So doing that becomes really hard. So then the common trick that you can do is actually you can look at the capsid and notice that if you look amongst naturally existing serotypes, the surface has these locations which are very variable and actually more amenable to changes. So a trick you can do is you can now insert into those surface exposed loops, and that allows you to screen a pretty sizable chemical space and look for new behaviors, and that's been actually quite productive. You can create engineered capsids in this way, and really most of the not Dyno ones are made in this manner. The challenge with that approach is you're not learning the rules to engineer the capsid as a whole, which is, in my opinion, and the thesis of Dyno, we think that's really important. We want to really learn how do you actually change the whole capsid so that you can make novel capsids. That's going to be critical to get to the brain as efficiently as possible. That's going to be critical to lower the dose like many orders of magnitude, which is going to have huge impacts on safety. It's just going to make it super, super safe. It's also going to have huge impacts on cost, because if the dose is just 100 times lower, your costs are just 100 times lower, and that could be really transformative. And then finally, also, one of the challenges of AAVs right now is the fact that once you get exposed to AAV, this could be, there's 3 of us, either 1 or 2 of us statistically actually have been exposed to AAV, and we have neutralizing immunity against it. So we couldn't receive a gene therapy. If you receive it in a trial, you're also going to mount a neutralizing immune response. Ultimately, what would be amazing is if we could have several vectors that are mounting immune responses that are different enough from one another that you could actually dose several times with AAV. So if we're right, and in a few years, there's many different drugs that are available with AAV, you don't face a trade-off of like having to choose just one because you have one ticket for AAV delivery, but you could actually, take on as many as you need or want.
So this is okay. That's very interesting. So one of the things that when we were at Advanced Therapies Week, Ben, Nicole Polk was talking about how one of the biggest problems in AAV is that when you change the payload, you have to change the capsid. I'm not super sure. I'm not an AAV guy. So if you had if you have a AAV therapy that you want to go to the brain, okay, and you have, gene A packaged in that, and then let's say you want to package gene B instead, and it's very different nucleic acid sequences. Do you need to optimize the AAV that granularly, or is that not a thing?
It would depend on where you're going. Are you going to the same space?
It's the same exact cell type, just a different gene.
So if you're going to truly the same cell type, then the same capsid should get you there again. Now, if your payload is sufficiently different, you might want to optimize the payload to like, the optimization that make payload A really good might be different for payload B. You might need to do that. That's also a place where AI models can actually help as well.
Mm-hmm.
But I think one of the promises of AAVs is this modularity, is the fact that the capsid and the payload are actually as the delivery system and the active component are as separate as any two biological things. If you look at antibodies, it's actually, the active bit and the delivery component are separate-ish. If you look at small molecules, it's the exact same thing that's going to get you both decide where you go and what you act. And interestingly, cells, which are the next layer of like complexity biologically, actually end up being more together because it's the same thing that is active and choosing where to go. So gene therapy is this special thing where you have the most modularity, and one of the opportunities is to exploit that by emphasize, like, we're choosing to solve just one of the modular components, and that's been really one of the key decisions we've made in building Dyno.
So on that note, do you think that the modularity is different? And if it's different, is it better or worse between like an AAV and a non-viral delivery mechanism?
I think that modularity applies generally to gene therapies, to genetic medicines, where you can benefit from solving the delivery question and then reapplying it. But the nuance will matter depending on your delivery vehicle.
Sure.
And the difference we've seen with AAV is it really works extremely well to get you to the nucleus. Like, the AAV does two things remarkably well. One is it will actually get its payload not just inside the cell, inside the cytoplasm, and many methods can get you inside the cytoplasm, but actually gets you all the way to the nucleus and expressing. That's really powerful. The other thing that's interesting is it's remarkably inert to the immune system, which is counterintuitive, because often a thing we hear about a lot is like, wow, AAV is very immunogenic. What is going on? The reason it's so immunogenic is because we use the doses. We have to use very high doses so that naturally existing serotypes are able to reach a therapeutic or near therapeutic level of delivery. But what's actually remarkable is if you're thinking about the amount of particles that are being injected, the fact that if you drop the dose by like tenfold, you have almost no immune response is kind of shocking. Like, there's very, very few biological entities that you could put in such a high number and have almost no reaction from your immune system. For most other viruses, like, the immune reaction would be lethal at like a much lower number. So it's something that's counterintuitive that's helpful to remember about AAV.
Interesting. So we're within a log in terms of dose between virtually no immune response and an immune response.
I think once you get into the details, your body is going to notice it. But I think when you're actually looking at the vector genome copies that we're putting in when going IV, the fact that it is as mild as it is kind of impressive.
Right. Yeah.
This is probably a little bit out of the scope of the conversation, but why do you think that is? That's very interesting biologically. Does it have to do with like the AAV? I mean, like, obviously it's the AAV itself, but is it some kind of like evolutionarily were we like less exposed to AAVs, or is our immune system just like not able to recognize them? What's going on there?
I think it's always hard to speculate about evolution, but in this case, it just seems to, you could imagine it is a evolutionarily viable strategy to be like, hey, I'm going to sneak in, I'm going to get to the liver. It's also important to remember that AAV itself is not a fully competent virus. It's adeno associated because it will only propagate in the presence of an adenoviral infection. So it's, just found this like very niche of like, I'm going to sneak in. There likely is some immune response to the adenoviral infection that time. But hey, I'm, my mental model of it is it kind of just wants to sneak in during that time. And part of it has been optimized to not being like super actively suppressed.
So real quick, again, forgive my naivety, but are there any kind of like pathological AAVs that exist? Is that maybe like there's just like they're not a threat to us, so we don't really care about them?
So when you look in the sort of broader family of viruses that AAV comes from, parvovirus has some pathogenic versions, like parvovirus B19, causes disease in kids, but it's not, AAV itself is, most people who've been exposed, you have no idea that you were exposed, and it just passes on.
Yeah. Well, the fact of the matter is we have thousands of viruses inside of us at any one time, and they're all mostly just harmless and inert.
Strange thing to remember.
A good chunk of the human genome is viral DNA, so we know that we've been being exposed to these things for millions of years, millennia at least.
Exactly.
But I kind of want to take the conversation into a little bit of a different direction real quick. Can we back up like 50 steps and just explain to this non-AAV person what are the major functions and major like biochemical sections of an AAV, and how much room do you actually have to play with these AI guided, designing of these things?
Yeah, so I think listing all the components is going to be hard, but in the span of this conversation, but I can give you a sense of like what happens. You can kind of break down the steps. So you have, and it's interesting because there's the step of first you actually have to assemble the capsid, right? So in a cell that for some reason has AAV in it, either because we are intentionally manufacturing AAV or because it's a naturally occurring infection, you're going to get the capsid components as well as the machinery that replicates the DNA component, and it assembles into a shell with the DNA on the inside, and then eventually like makes it out of the cell, either because again you're breaking the cells to extract the AAV and purify it, or it's being shed naturally during an infection. Then it's kind of interesting also what we actually understand biologically versus is still fairly mysterious. And this is a place where suddenly every serotype is going to be a little different. But we know that fundamentally there's going to be some entry into the cell where the AAV will bind some receptor on the surface of the cell and start making it towards an endosome. And we know that the AAV will notice that it's in an endosome and change, like because of the lowering of the pH, and change its conformation in a way to sort of make it into the cell. We're actually already getting into parts where if you look at different theories of how this is happening, you're actually going to see, we're at the edge of our understanding. But one theory is that it kind of is essentially able to escape the endosome and then traffics to the nucleus. Now we're getting into a part that's quite much less well understood of what's enabling that trafficking. By the way, that's a place where if we understood that really well, would also enable other forms of delivery, because we could repurpose that for non-AAV delivery components. And then the expression actually mostly has to do with the actual genome that's packaged itself. In terms of the room where you have to play, one thing that's interesting is once you start doing these experiments where you mutate every amino acid, you actually identify new biological functions. For example, in the work done in the Church lab, we found a second peptide. Turns out AAV is so compressed that you actually have peptides that are encoded in the next frame. So in the +1 frame of the nucleotide sequence, there's actually, like now we know of 2 different proteins that assist in the assembly of the capsid. And so, that reminder, biology is just super optimized. You have to deal with that when you're making it. But fundamentally, each of those steps, my intuition is each of those steps, there's probably a 5 to 10-fold increase in efficiency that I'd be surprised biology has already squeezed. And if we can engineer that increase in efficiency, that's how we could go to a place where, you're able to dose even the most engineered vectors that we have today, which are lower than ever before in terms of the dose they need. I think there's a lot of room to go, and that's going to be really exciting to get there.
Cool. Awesome. So we have a question here from Christian, so we want to get to that. So I'll just jump up my head here so you can see my mouth while I'm talking about it. Other than AAV, there are related parvoviruses that are also being investigated for use in gene therapy. I would be interested to know if Dyno is looking into these as well. Good question, Christian. Adrian, are you guys just focused on AAV, or are you looking at the wider parvovirus family, or can you say?
Yeah, I mean, I can tell you, I can tell you publicly, we're focused on AAV for now. That's because we think that's the place where a focused push in terms of technology development gets us to a place where you go from something that's occasionally useful in the clinic to, huge on a step change in terms of its use for gene therapy development. And we're we've achieved that step change with vectors that we've released and talked about publicly today, and we're looking, to push even further than that. But as I started at the beginning, I said, we're a genetic technologies company that for now is focused on AAV biology. And, we think, our platform of the types of measurements that we do and the type of AI guided design that we do is applicable across a set of technologies. I think the trick is we first want to really crack open delivery and then see what's the next bottleneck that builds on top of that.
Very good.
Yeah, that sounds good. I was going to ask if not different kinds of viruses, but different functionality, like even, different types of packaging different types of things. Is there any potential for expanding the repertoire of molecules that you can package in AAV, or is it just like biology has put a limit there?
Actually, there's been some really cool work presented. I saw it at ASGCT in the last 2 years. There's been proof of concept showing that if you do some clever tricks, you can get AAV to package RNA. You can also get AAV to package protein. You have to deal with the space constraints, but there's proof of concept there. It's that's been done. Question is, can you do it at scale and efficiently enough? But you've turned that from a is it possible scientific question into an engineering question that often typically as a field we're actually very good at.
Interesting. I'm an AAV guy, and for whatever reason, I've missed that people are working on RNA and proteins. That's nuts. But yeah, it is quite small, so you would be limited in the stuff you can get inside. But wow, that's really interesting.
So actually, can we pop this question up real quick? I was going to ask the same question. So he's asking if there's potential of combining capsid engineering with vector genome engineering, for example, cell-specific promoters. Do you guys mainly focus on the amino acid stuff, or are you also doing nucleic acid optimization? Yeah,
so far, most of what we've done has been on the amino acid part, but the question is correct. And you want to optimize all the components. You also want them working together well, not just be like good components in their own right, but also knowing that the combination actually works as well as you hope. You don't end up having a kind of like negative epistasis there. What we've seen is, so at Dyno, one of the things that's unique about us is we are working only through partners. So we are not developing our own medicines. We are instead working through a partnership model with companies of really any size. Often what we've seen is our partners often come with a pretty optimized payload, right? Like they have taken the payload and fine-tuned the promoter to target the right cells. They've done proof of concept experiments with the wild type serotypes. And often the component they really, really want to bring in is the capsid. So that's why we focus there. But, absolutely, we think about needing to optimize the whole package. And it's something that, we're working with partners to help enable as well.
Yeah, it's a really good model. Have you what are the trends you're noticing in terms of like requests and as far as like delivery? What is the most where is the field going? You should have a good idea, because you're going to be getting all kinds of like requests to deliver these things to different areas, right?
Yeah, I think what's maybe remarkable is how consistent the requests have been rather than like changing over time. But really, since we started Dyno, the list of things people have asked for has been remarkably stable of, get me to the brain, get me out of the liver, lower the dose, keep my manufacturing team happy by making it super, super easy to manufacture. That's always the sort of core set. That's where every capsid profile starts. But then the next step is often, thinking about how do you evade pre-existing immunity. That's becoming more and more top of mind especially as trials are dosing patients, or as trials are looking for being able to address not, half of the population, but the whole population. That's becoming higher at top of mind. One trend that I would say is kind of interesting is when we started Dyno, a big request that came up a lot was, can you fix the packaging size? It's kind of small. 4.7 kb, just not, there's a lot of things you can't do with that. That, I would say, is a request that has diminished in salience. And it's actually interesting.
Okay.
The draw, it's been even traditional payload engineering. We've just, we've shrunk Cas editors have shrunk to fit in AAVs. But also actually it's a place where AI tools, I think, offer a huge advantage, which is, can you take a very large thing, and can you actually achieve the same biological function while shrinking it, stick it in an AAV, has seemed to be working quite well. And I think a trend has been less of a focus on packaging size and more of a focus on the rest of the delivery piece.
That's hilarious. People are like, could you make AAV bigger? And you're like, that's like trying to ask me to make a Ferrari into a family van.
It's actually less crazy than it sounds, actually.
Really?
Because if you look at if you look at the wide world of viruses, there's viruses that have a fairly similar size in terms of the viral particle itself, or have similar components and actually package much larger things. So actually AAV just hasn't really, maybe because its sequence itself is just not very large, it hasn't optimized for how much it can package. And presumably there's some interesting low-hanging fruit in that space as well. And there's been interesting academic work going after that question. So it's less of a far-fetched idea than it exists, but it is dealing with the inside of the capsid, which is, like I said at the start, one of the harder parts to engineer.
Yeah. So on that note, that's really interesting to me. Then I just assumed it would be just a function of size, and if you're trying to turn a Ferrari into a family van, like you got to basically strip it down to nothing and try to build something brand new. But it really is a component of just it being poorly assembled inside. So this is a question. Just from my perspective, that would be super interesting. Then when you're looking at the inside of the capsid and you're using AI approaches to consider not just the outside that's going to be more associated with deliverability and whatnot, what kind of things have you seen when you look at the inside of that capsid and trying to optimize the sequence?
Yeah, I mean, I would say one thing we know is as you edit even deeper parts of the capsid, you change the overall conformation of the capsid, and that will have an impact on also the sort of exterior facing part. Ultimately, it does come down to generate the data so that you can inform the models to go after the hypotheses that you want. Because we've been so focused on kind of like what's that delivery piece, a lot of the action is on the surface, but what we've seen is you can create the conditions to make that engineering even better. At times means introducing changes in the sort of inside of the capsid as well.
Interesting. So I guess if we're coming back to the fact that you guys have been using AI for this entire process, what would you say really sets you apart in using AI to explore these difficult problems around the capsid structure of AAV?
Yeah, I think there's two components. One, which is a bit less relevant today, but is we were very early into, because we were so focused on this problem of AAV, we got to be some of the first exploring how different AI techniques can be applied to AAV engineering. Things like variational autoencoders, applying them to protein engineering, specifically AAV, but some of the first applications really came from our team and the academic work that backed our team. In terms of what sets us apart is, I'd say it's how we do both parts of the equation of generating the data as well as the models themselves. So, we've invested a lot of energy, a lot of effort into having really extraordinary models for the capsid engineering problem, and models that can really simplify things. Like if you want just making many changes on the capsid, yet have something that packages so that you have the opportunity to measure its properties and actually have a very good prediction for what those properties can be, our models can do that, and that's fairly unique. The other part is actually on the measurement capabilities themselves. We've invested a lot of effort finding just what's the right size of library so that you're not just detecting capsids that are interesting, but for every component of the library, you are measuring how it is doing, even if it's doing badly, because that information is often just as valuable. Like negative examples of, this sequence could have been good, but it's not, and this is how it fails. That data is also very relevant, and having that data in vivo is really critical and part of the kind of proprietary information that powers our platform that we've invested in building.
Dang, I was going to ask, how do you do that? I guess can you go into that at all, or is it all just like a black box?
So we've shared a lot of the, we've actually shared a lot of our even modeling approaches. We've published a lot on how we do this for AAV and for proteins in general, because we think, we're part of a community and we want to, advance together as a community. We've also shared a lot of information about how we do our capsid approaches, like the actual experiments themselves. One of the key components, for example, is if you're working with a barcoded library, meaning you have hundreds of thousands of AAV particles, and each particle of a given type packages a barcode of that tells you, hey, this is type 1, this is type 1000, this is type 100,079. One of the tricks that we found is extremely important is, can you add additional barcodes so that statistically every viral particle has almost a unique tag, so that you're actually able to count not just this is variant 1001, but this is actually one particle of variant 1001, and this is a different particle of 1001.
Oh,
when
right.
you do, though, that matters a lot, because you're actually able to detect that, hey, this variant, you have expression from two distinct viral particles that made it all the way to the genome and expressed. And that creates much higher quality data that you're able to use in the training of models, as well as in identifying the most promising capsids.
That's crazy. I love that.
Glad you like it.
Well, I guess just even to pick up on a point that you mentioned earlier too, you were saying the negative examples. This could have been a good capsid, but here's something that went wrong with it, and therefore it's failed. Don't use that again. It's interesting. A couple months ago, Jeff, we chatted with Yuan Hao over at Stanford. He was making a CRISPR GPT, where you can it's like this AI agent that helps you design CRISPR constructs for your specific indication. And he was mentioning such a big component of actually making this model sing was that they had the ability to gather all of this failed experimental data from all of these leading researchers, where they're like, that data is actually valuable. We need it. We need to teach the AI. Here's what doesn't work. Avoid this stuff.
Yeah, let me tap on that, because I think that's one of the most interesting things about AI engineering that's not always really front of mind, but for us it really is. One of the challenges, AI models are really, really good at interpolating. If you give it all poems ever written and you say, great, give me a new poem, boom, you're going to get, now we can all do this. We couldn't a few years ago, but now it's just doable. And they're pretty good, and they rhyme, and they're interesting. But actually, when we're doing these experiments, this applies in the space of CRISPR, it applies the exact same thing with AAV. You give it all of these examples, and you're asking it to do something much harder than say, give me another example. You're saying, give me something better than anything you've seen, right? You're actually saying, you've seen all the poems by all the great, now give me a better poem than all of them, right? And you can suddenly, you're like, ooh, that feels way harder. And that problem actually, another thing that's interesting is, when an AI model comes up with something new, we have this funny thing where if it's good, we're like, sweet. If it's bad, you're like, that's a hallucination. And what's interesting is you're actually trying to control the hallucination. You're trying to get hallucinations that are just kooky enough that they have the potential to be interesting, but they're not so all out that you're like, this isn't really even a poem anymore. It's just words. And so it turns out that in that process of calibrating, of finding this space where the models are still creative enough, but actually still are able to predict that this will be better, those negative training examples help a lot.
Interesting. So yeah, I guess on the topic of data, there is a question here from Victoria. What types of experimental data are most valuable for training AI models in capsid engineering? And do you consider that the current training data input is already optimized, or is it still an area that needs significant improvement?
Yeah, I think it, in terms of the experimental data, I'm, myself actually as a strong believer in the criticality of the experimental data. And in a simple way, what's most valuable is really the thing that most closely approximates what you care about. The more you can measure the thing you care about, the more that data will be helpful in designing things which improve on that property. It actually just happens to be very neat that for delivery, what you care about is expression in the brain. And you can go in and just measure expression in the brain. And with next-gen sequencing, you can measure it resolved across many variants. It's like a very convenient thing that we're applying here. In terms of the optimization, I think we're still very, very far from being completely done. I think this is also one of the core lessons of optimizing AI models for any application is that typically, if you can just find a way to cram more data into your training process, you're probably going to get better outcomes right away. Like, you can overthink the actual algorithm that's driving the thing, but maybe if you can just triple the data input, you're going to get better performance. And I think that's still extremely true in biology for AAV engineering, but honestly for all of biology. We are so, like, we think we're data rich because compared to 30 years ago, we're swimming in data. But compared to how complicated biology is, we are so data poor, which means that the value of really, really excellent experimental measurements that can be used to train these models remains extremely, extremely high.
Well, and that's the thing too, right? Like you just mentioned, there's a +1 reading shift has extra proteins in it that's used to assist AAV in its construction. So I mean, just the vast amount of data that we still don't know is something that really needs to be considered there.
What's really cool there, by the way, on that example, what's amazingly cool is just how quickly data shows you that, right? Because that sounds so trippy, but actually the way you notice that, like how do you actually observe that protein exists? It's actually very simple. If what you notice very quickly is you're like, wow, there's times when I introduce a synonymous codon change, but it has a huge impact. And you're like, how can that be? And then you notice that, like, oh, it's a synonymous change in the main frame, but in the +1 frame, you introduced a stop codon. And that is causal. And then you see, like, where does it do this? And you're like, oh, so there's a protein here. And, that's kind of the power that goes back to, get the right data and you can spot these patterns. Now, that's an example of a pattern that, like, a human can spot. It's, like, pretty easy to notice when you literally just stare at the figure. But the power of the AI techniques are they're just extremely good, like, pattern detectors. And they can notice, like, really, really subtle patterns and, like, bring them to the forefront and just identify, like, hey, there's this pattern is active. And whenever you notice that, you now have a choice. You can increase the pattern or decrease the pattern. And that's going to, in some cases do nothing, in some cases help or hurt. And now you have another lever you can pull in your engineering goal.
Love it.
So I want to kind of circle back. This is a great conversation, by the way. I'm having a great time. I want to circle back to the negative data. I think it just hit me how important the negative data actually is in these AI models, especially when it comes to these things. Because if we have 100 moving parts and we change all of them, right? And we say, oh, it looks like these, this characteristic on these 13 is good. That could just be a coincidence. But if we say these 13 are always good and these 4 are always bad, now it can begin to draw, like, 3-dimensional patterns, so to speak. But if we're not capturing that negative data, it's impossible to do that. And I'm wondering why that wasn't intuitive from the start, or was it? Now that now you and Yuhan, or whatever his name, I forget what his name was, but you both mentioned it as like a kind of an anomalous approach that you're taking. Is that a relatively unique thing to do, or is it just, like, not possible because of the limitations of data capture, or what?
I think it, ultimately you design an experiment, you're going to test, you're going to have a library. And if your library is randomly designed, you're going to get plenty of negative examples always. Mm-hmm. If your library is intentionally designed, it's kind of weird to, like, intentionally be like, hey, I'm going to actually step back and just make random changes and see what hurts. In practice, in biology, we don't know so much. So often it's very valuable to do that. It's often, there's other, the important trick actually is, if you have a model, the most valuable data is in training the next model is places where the model had it almost right, but got it wrong. So actually a place where it's saying, like, yeah, this will work. and then you make it and it fails. That feedback, well, it's sort of obvious if you just state it in this way. You're like, oh yeah, that's very valuable information. Stick that in the model. So you want to always find like what's the right amount of that to bring in.
I think it might just, like, to your point as well, Jeff, it might come back to just that idea, like, in the past, if you're going to be publishing a paper, you aren't going to publish failed experiments. But we're kind of living in this world now where that type of information is really valuable, where it might not have been as valuable in the past. Would that be fair to say?
I'm a bit of a purist, and I kind of disagree. I think if you had the library of everything everyone tried, we'd be in an even better place. You never know if they tried it in just the right way and it's worth doing again. But the fact that we don't publish our failures is it's kind of a crying shame of the biomedical field.
Yeah, definitely. Okay. There is one question from Christian. I want to get to that again quick, but just before that, so I wanted to just revisit quickly the immune response to AAV, right? 1 in 3 people already been exposed to AAV. If they get a gene therapy that's using AAV, likely going to get an immune response, and it's not going to be nearly as effective, if not at all. Do you think we can get to a point when it comes to designing a capsid with AI that we could make an AAV capsid that has no similarities whatsoever to AAVs that have been priorly exposed in humans?
I'm very confident in that, and for 2 reasons. One is ultimately the space of what counts as an AAV is shockingly large. And so here's a thought experiment. If you take naturally occurring AAVs, both of them are 700 amino acids and fold in essentially this very similar structure. But if you take 2 that are most distant, you can have some where they are different in more than half of their positions. That's crazy. Right, like that tells you that you essentially, like, the space of possible AAVs, even just with those 2, is effectively infinite.
Yeah.
And you actually have many of those examples. So actually, there's many choices we can make to the capsid, and that's like what evolution baked for us.
Yeah, that's
when
wild.
we get intentional about that, I think it's going to be totally possible. I think there's also other ideas that we can do, right? Like there's other ways in which you could cloak the capsid to prevent it from being visible to neutralizing antibodies. And then, of course, there's a lot of attention to, like maybe you don't even need to do this at the capsid level, right? Like there's ideas like IDS enzyme injections where you just degrade temporarily your circulating antibodies to have a phase where you can just be dosed with AAV. And if we can get that to work really safe and well, that's great. We just made AAV capsid engineering much simpler, and we'll take the win. But I think there's going to be many, like the combinations of these approaches is absolutely going to get us there.
Awesome. Okay, here's the question from Christian. Quickly here. In some applications, AAVs need to be optimized for multiple properties: good reproducibility, liver detargeting, high expression, etc. Can Dyno's AI models be trained to identify candidates that are optimal across multiple properties as opposed to just one?
I love that. I love that question. If you'd asked me to plant a question, I would have. Would have been on the list.
Well, now I'm suspicious.
The reason it's a great question is not only are AI models good for this. This is actually a unique feature that models have relative to evolutionary selection experiments. And actually, what I mean by this is if you set up a screen where what you're going to measure is binding to some receptor. Physically, that is the only thing you're going to screen. And there's this kind of saying in the screening community that you get what you screen for. And the tricky part here is if what you screen is binding to this target or reaching this tissue, you are not actually actively selecting for, is it fine to manufacture? Does it go elsewhere? And you actually can't physically create that selection pressure. I mean, you can do rounds of it, right? You can do one round that goes to the brain, then one round that goes away to the liver. But each time you might not get things that like actually build on both.
Yep.
That's one of the beautiful things when you move to the computational realm, which is that in the computational realm, even though these things are distinct properties, what you can actually say is consider a meta property that is good at this, and good at this. And I just want you to design vectors that are better at both. And the AI models actually do this like remarkably well. Driving towards, for example, liver tropism while improving brain tropism while decreasing liver tropism while maintaining packaging. It's something we've seen, time and time again.
That's a great point. Yeah. No comment on that.
Awesome. Okay, so I guess we're getting here close to the end. We want to be respectful of your time, Adrian, but just a couple questions to finish off here. Where do you see AAV in the year 2030?
2030 feels close, but I'm hoping that 2030 is a time when we are looking back at now and we're like, why did we have any doubts about AAV? Because it's just blasting through the clinic. That's where I would hope to be 2030, because of clinical timelines being what they are. And by the way, that's one thing that as a community, we need to fight to get our ability to move through those milestones faster and cheaper, because that's going to create more momentum for us to get the drugs to the patients that need them. I think 2030 is a time when we're really feeling that momentum. And that's because I think the conditions are right for it. Like, we have the foundational components in place on AAV, which is what we work on, but also what our developer partners work on in terms of payloads and in terms of having the diseases where we essentially know that you go in, you have this intervention, and your likelihoods of success are anything that we've seen in drug development before. And, I hope in 2030 we're, making the most of that moment.
Fantastic. I think it will be interesting even from that perspective clinically. I think we will see some pretty interesting changes over the next few years, just with regards to how quickly something can progress through the clinic. I'm quite hopeful that AI will come into that process. You see some interesting regulatory shifts that are taking place across the world that are really saying, hey, if we've got some sort of rare disease, let's try to get this into sick kids as quickly as possible, because they don't have the time to wait. So yeah, it makes me optimistic overall. Fantastic. Well, I guess that's all the questions I've got for now. Adrian, really appreciate your time. I guess just here at the end, do you have any final thoughts? Any events that you've got coming up that you would like to invite people to, or anything cool that people should be watching for Dyno Therapeutics in the next couple months?
Yeah, I think the main thing I want to draw people's attention to is really a combination of two things. Is we announced this at ASGCT earlier this year, a program from Dyno to make it as easy as possible for startups at any stage, from the very earliest to more mature biotechs, to be able to access our technology and to work with it. We called it the Frontiers program, and this was in response to something we saw in the field where we saw, like, if you're a gene therapy developers, you've invested a lot of effort in making a really innovative payload, but to actually get the benefit of that payload, you have to pair it with innovative delivery, and there's barriers to access that. And our response to this was with the Frontiers program to just dial down those barriers down to zero. So for the AAV gene therapy development community, if you want access to our capsids, check out the Frontiers program. We've been really impressed by the traction the program has had and all the attention, but I know there's more and want to bring that on. And then also we've announced a conference that's occurring in Boston in November. It's a very small conference, so it's invite only, but we encourage folks to apply to be on the invite list. And the conference we're really trying to bring the full stack of the community, from the gene therapy developers to AI model makers to patients and their advocates. And we already have a really exciting a roster for it that's planned, and hoping more people join.
Right on. Excellent. Well, again, Adrian, thanks so much for your time. Always great to talk shop on AAV. Thanks again, everyone who's come today. Thank you for your questions.
Yeah, thank you for the
questions. See you
questions.
next time. Bye, everyone.
Thanks.
We'll get you to stay on for a second there.